Enjoy chapter 12, chemistry. So let's get going. Come on, you. There we go. All right, chemistry 3111. I made YouTube videos that covered the content for sections 12.1 through 12.4. I expect you to take a look at those, as I won't be going over all those sections in detail during the synchronous lecture. Again, that's why I prepared the videos. However, there are a couple major reactions that were covered in those sections, and the major reactions that you need to know from section 12.4 are how to reduce a ketone or an aldehyde. And we learned two new ways to do that, or two new reagents, I should say. One of them was to do sodium borohydride reduction. And sodium borohydride is a weak enough reducing agent that it can be used in the presence of a polar protic solvent. Here they have methanol. You could also use ethanol as a solvent, and we can even use water as a solvent. So ethanol or water would work as well. There's a stronger reducing agent that I covered in those lecture videos, namely the chapter 12.4 video, and that is using lithium aluminum hydride. And lithium aluminum hydride is a much stronger reducing agent, and so it can't be used in the presence of water. It is used in other solvents because lithium aluminum hydride is very reactive in the presence of water. It can actually start a fire in the presence of water, and that is why you have to know that the first step is lithium aluminum hydride. And then the second step is that we add water to add the proton to the alkoxide. And you can use water, or you can even use H3O plus here. Either one is totally fine. And what's really neat about these borohydride and aluminum hydride reagents is that you can reduce a ketone or an aldehyde in the presence of an alkene. And the alkene doesn't get reduced because if you use the other method of reduction of a ketone or aldehyde, which is just plain old hydrogenation, well, we learned way back in the alkenes chapter of Organic Chemistry 1 that an alkene can be reduced in the presence of hydrogen with a catalyst like palladium, platinum, or nickel. And so you see here, you get two for the price of one. You reduce the ketone, but you also reduce the alkene. Now, if you want to do that, well, then this seems like a great course of action. However, oftentimes we'll want to reduce a carbonyl group and keep that alkene intact. And so in that case, either one of these reagents would be the better choice. And those are three of the major reactions that were covered in those YouTube videos. Another thing I want to mention before we move into new content is that lithium aluminum hydride is so strong as a reducing agent that it can also reduce esters and carboxylic acids. The difference is that instead of just putting lithium aluminum hydride as our first reagent, we have to let the reader or viewer know that we have to add excess lithium aluminum hydride followed by water, or you could put aqueous acid, so you could put H3O plus here. But what that does is it reduces a carboxylic acid or an ester all the way down to a primary alcohol. So we always end up with a primary alcohol. So there we go. We learned lithium aluminum hydride reduction of an aldehyde, ketone, an ester, or a carboxylic acid. We saw that sodium borohydride is a weaker reducing agent. It can reduce an aldehyde or a ketone. And then we saw that hydrogenation can be used to produce not only an alkene, but a ketone or an aldehyde as well. Well, let's move on to new territory and let's talk about diols. And there's a very short section here, 12.5, dealing with diols. And the first section, or the first part of this chapter, 12.5, covers naming diols. It says that when you name a diol, diols are named using the same method as alcohols, except the E is not dropped from the alkane name, and the suffix diol is used. If you think about, if you have, for example, 1, 2, 3 carbons, we call that propane. So that's propane. But if you make an alcohol, you'd call this 1-propanol, right? You drop the E. There's no E in there. However, if you have propane again, and you add an alcohol to either end of it, you make a diol, and you don't drop the E. We have to provide a locant for each hydroxyl. We would number this 1, 2, 3, and so you'd call this 1,3-propane diol. We have another compound here. We have hexane as our longest carbon chain. 1, 2, 3, 4, 5, 6. And we want to number it in such a way that we give the first hydroxyl the lowest possible number. And hence this compound would be 1,5-hexane, without dropping that E, diol. Whenever you hear that word glycol, and you might have heard this whenever I've mentioned ethylene glycol or propylene glycol in class, glycol is a term that is used to describe a compound that has two hydroxyl groups in it. And one of the most common is ethylene glycol. And why is ethylene glycol so common? It's because it's used as automobile antifreeze. And so if you are driving a car, which most of us do, have a car or a truck or something, you're going to have coolant in the engine. And ethylene glycol is one of the components of coolant. Another component that's very common in engine coolants would be if we take propane and if we put a hydroxyl on one carbon and then put a hydroxyl on the second carbon. We call this propylene glycol. I'll scribble this in here. Propylene glycol. And both of these, again, are found in automobile antifreeze. Anyhow, so there you go. A little bit about diols and how we use the word glycol and two of the most common glycols, ethylene glycol and propylene glycol, which will show up throughout the course. And those are both found in automobile antifreeze. All right, well, let's move on and take a look at how you would make a diol. How would you make a diol? Well, probably the easiest way to make a diol, besides dihydroxylations of an alkene that we learned in Organic Chemistry 1, would be to reduce a diketone. Here we have a diketone, we have a ketone here, we have a ketone here, and we can use any one of those reduction conditions that we learned earlier on in the chapter that we use to reduce a carbonyl compound, be it an aldehyde or a ketone. We could use hydrogenation using hydrogen, palladium, platinum, or nickel. We could use lithium aluminum hydride reduction. Again, keep in mind that's a two-step reaction. The first step is to treat it with lithium aluminum hydride. The second step is to treat it with water or H3O+. I also want to mention that this second step here, we refer to this as the workup step in this reaction. Or you could use sodium borohydride reduction. And what's important for you to know is that is all done in one pot. You don't add things separately. You just add the sodium borohydride and the methanol simultaneously. You know, another thing that I was just thinking of, whenever I'm lecturing, I'm always thinking of a couple things at once, is I don't remember if we looked at this dicarbonyl compound, but I was just thinking, you know, how would you make this compound? If you have 1, 2, 3, 4, 5, 6, 7 carbons, like that, so 1, 2, 3, 4, 5, 6, 7. Yeah, so let me see here. 1, 2, 3, 4, 5, 6, 7. Yeah, the way that you would make this compound, or the way that I would make this compound, would be from this compound, if you had something to look like this. So there we go. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, if you took this compound, so this is 1,2-dimethylcyclopentene, and if you first treated that with ozone, and since it's an alkene, in the second step you treat it with DMS, that would give you that diketone. So just kind of a fun thing there. Anyhow, moving on, this is just nothing more than review. So this is a review of Chapter 8. We learned a couple of ways to make diols. Namely, we learned how to make a trans diol. So we learned how to make a trans diol, and that is made by anti-dihydroxylation. And we learned how to make a cis diol, and that's done by syn dihydroxylation. You need to have both of these conditions at your fingertips. They were learned in Organic Chemistry 1. However, we did review them in Chapter 11 at the start of this course. So first one is to treat an alkene with a peroxy acid like MCPBA, or you can just write RC3OH. That's totally fine. You make an epoxide, and then you open that with aqueous acid. If you want to do a syn dihydroxylation, we learned a whole bunch of different ways to do that. However, the most common way that we see in our textbook is to use a catalytic amount of osmium tetroxide. which is great that we're only using a catalytic amount because osmium tetroxide is so toxic. And then in the second step, we use NMO, or N-methylmorpholine N-oxide, as our co-oxidant. So that serves to regenerate the osmium tetroxide over and over. So preparation of diols. So what have we covered here? We learned how to make a diol from a diketone by reduction, or we looked at a review, really, nothing more than making a diol from an alkene, and we learned how to make a trans or a cis diol via anti or syn dihydroxylation, respectively. All right, well, let's move on and take a look at section 12.6, which deals with what is called the Grignard reaction. So the Grignard reaction, or it says here Grignard reagents, and Grignard reagents are often used in the synthesis of an alcohol. What is a Grignard reagent, you might ask? Well, first of all, you might be wondering, is that name pronounced correctly? Shouldn't it be Grignard? No, something like that. Well, Victor Grignard was a French chemist, so technically his name would be pronounced Victor Grignard, okay? But anyhow, in English, we just call him Victor Grignard. And Grignard won the Nobel Prize. We should write this down. I mean, Nobel Prize, somebody should remember it. Grignard won the Nobel Prize in 1912. So it's a while ago that he picked that Nobel Prize up. However, he won the Nobel Prize for the chemistry that we're about to cover. However, he did all kinds of interesting research in chemical warfare in World War I. He developed the use of phosgene as a chemical, as an agent in chemical warfare, and also mustard gas. Anyhow, we're not really concerned about phosgene or mustard gas today, but we are concerned about the Grignard reaction, and I'm going to explain to you why Victor Grignard won a Nobel Prize. What makes this chemistry so great? First thing, before we get into the reaction, we need to learn how to make a Grignard reagent. You remember alkyl halides, like an alkyl iodide or chloride or bromide? Well, all you have to do is take an alkyl halide and treat it with magnesium metal, and what happens is the magnesium kind of sticks itself right in between. Let me go back here. I'm losing my place. Here we go. The magnesium kind of inserts itself in between the carbon atom and the halogen. You might be wondering, well, how the heck does that happen? Our textbook doesn't cover that. If you wanted to do some research, I'm sure you could find some information about that, but we refer to that as insertion. Anyhow, the magnesium sticks itself in between the carbon and the halogen, and we make what's called a Grignard reagent. I have a couple of examples here. If you take bromobenzene, shown right here, bromobenzene, and you treat that with magnesium, and of course this is done in the presence of a solvent. Oftentimes it's done in diethyl ether. So we'll just write diethyl ether here. You can use other solvents, but ether is very common. What you get is the magnesium stuck in between the aromatic ring and the bromine. And this, you would either call this phenyl, so I'll write it down here. You'd call this phenyl magnesium bromide, or if you want the shorthand, you could call that a phenyl Grignard. Phenyl Grignard, because when you have the magnesium bromide, people know that this is a Grignard reagent. The same thing applies on the other side here, on the right side. If you have 1-chloropropane and you treat that with magnesium, again, in an ether solvent, you end up with propyl magnesium chloride. So again, you could call this propyl magnesium chloride, or you could just call it propyl Grignard. I'll use the red pen here. Or you could call it a propyl Grignard. Why? Because when people see the magnesium chloride here, they know you are talking about a Grignard reagent. Something interesting about this bond between a carbon and a magnesium. What's the electronegativity of a magnesium and a carbon? Well, let's take a look here. It says here there's a pretty good difference in electronegativity between carbon and magnesium. Carbon has an electronegativity of 2.5, and Magnesium has an electronegativity of 1.3. And so the difference in electronegativity between the two, would be 2.5 minus 1.3, which is 1.2. Now that falls in the range of being a polar covalent bond, because our textbook states that a ionic bond is having, when we have a difference of electronegativity that's greater than 1.7. However, most of the time, I will draw my Grignard reagents like this. Okay, I'll draw them in this way, and you might be wondering, well, why do you draw them that way? The reason why is because if I draw it as an ionic compound, it allows me to focus on the lone pair of electrons on the carbon. So I basically have an aromatic carbanion or a carbanion here, and that carbon anion can function as a great nucleophile, or it can be a strong base as well. All right, somebody asked me, is there another abbreviation that you can use for these? Absolutely, okay, absolutely. Instead of writing out an entire aromatic ring, you could just say PHMGBr. That would just be a condensed form of this. And if you go back here for this propyl magnesium chloride, you could just write propyl magnesium chloride. Again, that's just a shorthand. Okay, there's nothing wrong with either of those. They all mean the exact same thing. So again, repeating myself, we have a negative charge on a carbon. And what does that mean? It means the carbon can behave as a nucleophile or a base, either one. So we can use that to our advantage. Let's take a look. And Grignard reagents kind of react like something like lithium aluminum hydride, in that negative charge on the carbon can attack a carbonyl of a ketone or an aldehyde. Let me just zoom in here on this mechanism. And I'm going to write here so that you know, you must know this mechanism. You have to know the mechanism of the Grignard reaction. So here's my Grignard. This is my Grignard reagent. Okay, I left out the magnesium and the bromide, or the author of the textbook did. And the Grignard reagent, again, is a very strong nucleophile. So we'll put here strong nucleophile, and a carbonyl is a good electrophile. Why is that? Because the carbon is delta minus, the oxygen is delta minus, and the carbon is delta plus. So we have our nucleophilic attack occurring here, and we end up making an alkoxide. Once we form the alkoxide, so this is the first step, this is step number 1. In the second step, we treat it with water or aqueous acid, and that serves as a proton donor to make an alcohol. So why did Grignard win a Nobel Prize? He won a Nobel Prize because of this right here. That when the Grignard reagent acts as a nucleophile, it forms a brand new carbon-carbon bond. And whenever a scientist can develop a new way to make a carbon-carbon bond, that person will always live on in infamy. And it says here the key difference between LAH, which only adds a hydride, with a Grignard reaction, which adds a carbon nucleophile, is that now you make a brand new carbon-carbon bond. And that is why Grignard won the Nobel Prize. And that's why we're still talking about him 110 years later. And that's why 110 years from now, people are still going to be using the Grignard reagent and Grignard reagents and the Grignard reaction, because it's such a great way to make carbon-carbon bonds. Extremely, extremely useful. Now, there's something I want to point out to you, and that is, as David Klein, the author of the textbook, has released new editions of the textbook, he makes small changes. And one small change that he has made from the first, second, and third edition to the fourth edition, which is the edition that you guys have, is that instead of just adding water in the second step, oftentimes he'll put H3O plus now. And I think he put that in because a lot of people are saying, well, usually when you do Grignard reaction, you don't just add water in the second step. You usually put in a buffer that's going to have an acid in it. So something like H3O plus, a weak acid, is even better. And again, this is what we call that work. We call that the workup step. Sorry, I can't see here. Workup. Okay. All right. So there you go. Grignard reagents and the Grignard reaction. Super useful chemistry. Why? Because you make new carbon-carbon bonds. Up until now, up until this moment, the only way that you had ever learned to make a new carbon-carbon bond was to take a terminal alkyne, deprotonate it using sodium amide, and then treating it with an electrophile like methyl iodide or something. Now, what's interesting about the Grignard reagents is since they're not only nucleophiles, they're really strong bases, you have to be very careful about the reaction conditions, meaning that you have to be sure there's no source of an acidic proton when you're running the Grignard reaction. Well, where would I find an acidic proton? I mean, even water is going to act as a strong enough acid to protonate a Grignard reagent and destroy it. So what that means is when you do Grignard reactions, you usually have to dry your glassware in a drying oven. So that removes all traces of water from the surface of the glass, which is made of silicon and oxygen. So check this out. It says because a Grignard is both a really strong base and a strong nucleophile, if it's exposed to water at all, and I mean even water from the atmosphere or an alcohol, it's just going to rip the proton right off of that, and it's done. Your Grignard reagent is toast. So let's say you bought a Grignard reagent from a chemical supplier, you spent, a few $100s on it, then you try and do a reaction with it, and there's water in your reaction, even if it's just slight, ever so slight, just a few molecules, and it's going to destroy it. Check it out. Here's your Grignard reagent right here. And let's say you've got some water in your flask. Well, the Grignard is a base. It's going to remove a proton from the water to produce the alkane. Okay. Now, if we compare the pK of water, which is an acid, and the conjugate acid of the Grignard reagent, you see that the alkane has a much higher pKa, and we know that the equilibrium is going to lie hard to the side of something with a pK of 50 compared to something with a pK of 15.7. We're talking greater than 10 to the power of 30, okay? So that is why when we do the Grignard reaction, we usually use anhydrous ethers for a Grignard reaction. So what does that mean? It means that the Grignard, whatever solvent you're using, your ether usually has to be distilled or put over some kind of drying agent, something that's going to remove any trace of water. If you're wondering what kind of ethers are good for a Grignard reaction, the ones that we usually turn to are diethyl ether. So we could just write diethyl ether like this, which we usually just abbreviate ET2O, or we like to use a cyclized version of diethyl ether, which is this here. And this compound has a name. This is called THF, which stands for, I'll put right here. THF stands for tetrahydrofuran. So tetrahydrofuran. Diethyl ether and tetrahydrofuran are the ethers that are most commonly used for Grignard chemistry, and they're usually dried before you use them. So distilled in some way to remove all traces of water. You can imagine it's better to do Grignard chemistry in a state like Colorado than Oregon or somewhere on the coast. All right, so let's see here. Let's take a look at some Grignard examples. First one shows cyclohexanone, which is this cyclic ketone being treated with methyl magnesium bromide, followed by water. And again, you could also write H3O plus. I would accept that. And so what happens is we end up adding that methyl group and making an alcohol. And this time we're taking that ketone. So we're starting with a ketone, and we're making a tertiary alcohol. In this one here, we have an aldehyde. And when we take an aldehyde and we do the same thing, so aldehyde, and we treat that with methyl magnesium bromide or methyl Grignard. And Sandrina, you could also call that Me, MGBR, means the same thing, or CH3 or GBR. And then water or H3O plus. Now we take the aldehyde and we convert it into a secondary alcohol. Aldehyde will always give you a secondary alcohol. And check this one. This one's even neater if you ask me. This is where you're starting with an ester. So starting with an ester. And if you take an ester, you can't just use one equivalent of the Grignard reagent. You have to use excess of the Grignard with an ester. And when you do that, you end up making a tertiary alcohol because the Grignard ends up adding 2 times to the ester. So we'll put here adds, we'll put here adds 2 times. And if you're wondering what that mechanism looks like, I don't know if I put it in here or not. I don't know if I did, but it's definitely in the textbook. So I'm going to write it here. I'll put down here C mechanism in textbook. All right, and if we have time, we'll do a problem where we can check out that that mechanism. You know, just something else that popped into my brain here while I'm lecturing along. Besides not being able to use a Grignard in the presence of water or an alcohol, I'll just throw in one more thing here. You also can't use a Grignard in the presence of a carboxylic acid. So we'll put here, or carboxylic acids. And the reason why is this exact same reason. If you have a Grignard in the presence of a carboxylic acid, well, let's say your carboxylic acid, we'll just write something like this. It's got a pKa of around 5. Okay, well, when that gets deprotonated, you're still going to end up with an alkane, and that's an even bigger difference. Now we're talking about 10 to the power of 45. So you also can't use it in the presence of a carboxylic acid. It'll just rip the proton off of the acid. Okay, well, let's take a look at a practice problem here. It says, show how a Grignard reaction can be used to make each of the following compounds, starting with an aldehyde or a ketone starting material. If we take a look at the first one, it's a tertiary alcohol. And remember, we want to start with an aldehyde or a ketone, not an ester. And we've got a tertiary alcohol. We've got 2 methyl groups, so those groups are identical. And then we have a propyl group over here. So that means we could either use methyl magnesium bromide or we could use propyl magnesium bromide. But we need to figure out what would the starting ketone or aldehyde look like that I would either add methyl magnesium bromide or propyl magnesium bromide or chloride to. So let's start out with, why don't we start out with having the 2 methyl groups intact and then figure out what it would look like when we add propyl magnesium bromide to it. Well, again, if we were to cut this bond here, what would the starting carbonyl look like? It would have 1, 2, 3 carbons, and it would have a double bond to the oxygen. So our starting material would be acetone. You'd have to start it with acetone, and then in the first step, you would treat it with propyl magnesium bromide. And you can draw it this way, showing a covalent bond here, or you could erase this. You can erase that, and you can put the negative charge in here if you like that. There's nothing wrong with that at all. In fact, it's really handy to do that because then you can practice your mechanisms. You can say, well, this is going to attack my carbonyl, and that's going to produce this alkoxide. So I'll draw this like that. Here's my alkoxide. Then I have my 1, 2, 3 carbons here. And then in the second step, I'm going to treat that with H3O plus. So H3O plus, like this. And then this is going to rip a proton off of here. Left out some lone pairs, didn't I? Anyhow, and then that is going to give you the product. Now, if you were to use methyl magnesium bromide instead, what would that look like? What would that look like? Well, in that case, you'd end up having 1, 2, 3, 4, 5 carbons, and you'd have the double bond to the oxygen like this. And that compound is called 2-pentanone, which is neither here nor there. Well, you have 1, 2, 3, 4, 5. You'd have the double bond to the oxygen here. And what you would do is first you would treat that with methyl magnesium bromide. And then in the second step, you would treat that with H3O plus or H2O. And then that would give you the desired product. Okay, so two possible ways to make this compound. Give me a thumbs up if you follow me on that. Or interrupt me if you have a question. Okay, this is just the solution to B. There's two possible ways. Okay, again, don't hesitate to interrupt me if you have a question. Let's try one more. Let's try, because you have the solutions to all of these in the solutions manual. Let's try D. Okay, in B, it didn't bring up anything to do with stereochemistry because it's not a chiral molecule. However, in D, it says we want to make this compound, but it's racemic. Okay, so first let's imagine if we had ethyl magnesium bromide. Well, in that case, you'd have the double bond here, and we'd be starting with an aldehyde. So you'd start with this compound, which looks like this. And then in the first step, you treat it with ethyl magnesium bromide, followed by H3O+. Oops, move that over. So second step is to treat it with H3O+ or H2O. And keep in mind that since this carbon is sp2, it is trigonal planar. Therefore, my nucleophile, my ethyl nucleophile from my Grignard reagent can attack from the front face of the molecule, or it can attack from the back face of the molecule, either side. So I end up with a racemic mixture, a 50-50 mixture of enantiomers. And of course, once you do that, it's going to give you the product. Now, what if I wanted to add this group over here? Okay, if I wanted to add those 7 carbons that are in that red box, well, what would that look like exactly? Well, I could have a Grignard reagent that looks like this, where I have my aromatic ring. And here we go, like this. Then I could have, my magnesium bromide like that. That would be my Grignard reagent. So this would be my first step. Let me just move this over here. Like that. So what would my aldehyde look like? In this case, my aldehyde is only going to have 1, 2, 3 carbons. So this compound is called propionaldehyde. We'll learn how to name aldehydes later this semester. And then in the second step, I'm going to treat that with H3O+, and that's going to give me the product, just like that. So we've covered B and D. C and E are very, very similar, except for in E, there's 3 different ways to make the compound, because you have an ethyl group, you have a methyl group, and you have a butyl group on there. So there's 3 different ways to make that compound, but the rationale is the same in all of them. You're starting with a ketone or aldehyde. You're treating it with the Grignard reagent, which is a nucleophile. It attacks the carbonyl, and then you protonate it to make an alcohol. If you're starting it with an aldehyde, then you always end up with a secondary alcohol. And if you're starting it with a ketone, then you end up with a tertiary alcohol. All right, any questions about that? If not, we're going to move on to a nuance of Grignard reagents, and that we already discussed that you cannot use a Grignard in the presence of water, a carboxylic acid, or an alcohol. Well, that's kind of a bummer, because alcohols show up in organic compounds all of the time. So what if you wanted to do a Grignard reaction with a compound that had an alcohol in it already? What does that mean? Let's take a look here. Look at this reaction. Let's say you have this compound here. It's got 2 functional groups. It's an alkyl halide, but it's also an alcohol. Now, if you were to take that and treat that with magnesium and form this hypothetical Grignard reagent that cannot be formed, this is not reality, but just imagine if you could, then that Grignard reagent could also be drawn in this way. All right, so like this. Okay, I'm just redrawing it, showing the charges, and then that's going to act as a nucleophile like this, and then we could protonate it to get this product. What's the problem? The problem is this proton, right? That's an alcohol, which has a pK of around maybe 15, between 15 and 18. Therefore, the Grignard reagent, let me just remove these curved arrows here, is not going to act as a nucleophile. What it would do way before you get a chance to do that is it is just going to take that proton and rip it off like nobody's business. And therefore, your Grignard reagent is destroyed. If you did that, you would end up with 1, 2, 3. You just end up with this, 1 propanol. Oh, gone, right? Incompatible. The alcohol acts as an acid, so it is incompatible with a Grignard reagent. So what do? Well, what we can do is we can mask the functionality of that alcohol. Another way that we could describe it is we say we protect the alcohol. So we can cover this alcohol up somehow so that we can form the Grignard reagent, make our desired product, and then we can remove the alcohol in the last step. Check this out. How do you protect that alcohol? Well, I guess before we do that, here's the description. What we need to do is a 3-step process. The first thing we need to do is add a protecting group to mask the functionality of that alcohol, to basically prevent the acidic proton from being removed. Then we want to do our Grignard chemistry, still have our protecting group, and then we want to rip it off at the end. Well, let's take a look. Organic chemists are great at finding all kinds of ways to get reactions to work when they want them to do it. And so one such protecting group that we can use to mask the functionality of an alcohol is a trimethylsilal ether. So this is a type of what we call a silyl ether, because the silyl ether has an R group, then an oxygen, and then a silicon, right? Silicon for the silyl group. Anyhow, so what we do is we take the alcohol here and we make a silyl ether. And the silyl ether that we make is a trimethylsilal ether. So instead of having the oxygen bound to a hydrogen, now it's bound to a silicon. And the abbreviation or the acronym that we use for the trimethylsilal ether is we call it a TMS group. So instead of OH, we have OTMS. There's our silyl ether. Now, how do you make the silyl ether? The way that you make the silyl ether is to take the alcohol, here's our alcohol, to treat it with trimethylsilal chloride. So TMSCl stands for trimethylsilal chloride. And we also not only add the alcohol in the trimethylsilal chloride, but we also have it in the presence of ET3N, which stands for triethylamine. So make sure you know both of those acronyms. And triethylamine just acts as a base because when you do the silylation, you end up producing HCl, and then the HCl gets neutralized by the base, right? Because an amine is a base. And then you end up making triethylammonium chloride. So you don't have any strong acid sticking around. What's neat about the trimethylsilal chloride and the alcohol is that the mechanism is SN2. Check this out. It says here, the evidence suggests that when the alcohol reacts with the trimethylsilal chloride, it actually occurs via an SN2 mechanism. Then you might be going like, whoa, 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 that's not true. How would that happen? Isn't this silo? Isn't the silicon tri-substituted? I thought that when we had something that's tri-substituted, a trialkyl something like a tertiary carbon, then that is not going to react via an SN2 because it's too sterically hindered. Well, if you look at silicon, it is found below carbon in the periodic table, right? If you look at group 4A, you have carbon, oops, I got chlorine on the brain, but anyhow, and below that, then you have silicon. And silicon, since it comes down lower in the group, what does that mean? It means it's a bigger atom. And since it's so much bigger and the bond is longer between the silicon and the chlorine, what it does is it renders the nucleophilic attack not sterically hindered. And so the nucleophile can attack from the backside, which is different than what we saw with carbons. But hey, atoms do what they're supposed to do. And silicon is so big that when you compare the space-filling models of tert-butyl chloride and trimethylsilal chloride, you can see here that we have no room, but here it's like open for business for that nucleophilic alcohol to just go in there, and the alcohol is going to, The alcohol, where am I here? There we go. The alcohol is just going to attack the silicon from behind, and then the chlorine is going to leave. Now, if you're wondering, okay, I understand how to make the trimethylsilal ether, and I understand that that is robust or stable in the presence of the Grignard reagent when it's formed, but how do you remove it? How do you get rid of it? Well, the way that you remove it, the silal ether, is that you treat it with a source of fluorine atoms. And if you're wondering, well, where do I get some fluorine atoms? Well, one place that you can get them is from this compound here, which is called TBAF, or tetrabutyl ammonium fluoride. So TBAF is very commonly used because there's a very strong bond between silicon and fluorine. And that's what happens. The fluorine ends up attacking the silicon. Another option is just use plain old acid. You can use aqueous acid. The only caveat with that is if you have some kind of group in the molecule that's labile to acid, well, then it wouldn't be your best choice. So now let's take a look at the whole reaction of doing a Grignard reaction in the presence of a protecting group. So check this out. Here is an overall process. Here's how you'd make this molecule from this molecule. The first step is we're going to protect the alcohol as a silal ether. We do that by treating it with trimethylsilal chloride and triethylamine. Now you can treat it with magnesium to make your Grignard reagent. So now you've got the Grignard reagent formed in the first step, and you still have your silal ether intact, and that is going to act as a nucleophile and attack the carbonyl. But again, since the silal ether masks the hydroxyl functionality, you don't have to worry about any side reactions. Then in the last step, you treat it with water or aqueous acid, and there you go. You've done the Grignard chemistry. And the last step is just like in the, like the last scene in Scooby-Doo. They always say, like, and now I'm going to show you who's underneath the mask here, the criminal, So to deprotect it, you treat it with TBAF, or you could treat it with a mild aqueous acid, and that will remove the silal ether, and that's all there is to it. Our textbook goes over a few protecting groups. So the TMS ether is the first one you learn, and we learned several more throughout the organic chemistry too. But there are books written just about protecting groups in organic chemistry. Very common for chemists to know hundreds of different protecting groups. Very important in organic chemistry. Well, with all that information in our brain, let's see if we can come up with a synthesis of this compound, starting with this compound, which has a bromine in it and an alcohol, and we want to use some Grignard chemistry. It says here the following transformation involves a Grignard reaction and uses a protecting group. Identify the reagents that can be used to achieve the transformation. The first thing I notice is that we're going from a final product, starting with a compound that has 7 carbons, and then we're ending up with something that's got 6, 7, 8, 9, 10 carbons, and that means we have to add these 3 carbons here. Well, if I can insert my magnesium in here to make my Grignard reagent, what that would mean is that my ketone, since I have a tertiary alcohol, the ketone I'm going to need to react my Grignard reagent with would be acetone. And so I think we all know how to make how to make the Grignard reagent. We just treat the aryl bromide with magnesium. However, we've got this pesky hydroxyl group to deal with, and we've got to protect that first. So what's our first step? Our first step is going to be converting the alcohol into a silal ether. And for that, we use trimethylsilal chloride, triethylamine together, and that gives us the silal ether. Now we don't have to worry about the acidic proton on the alcohol, and we can just go ahead and make our Grignard reagent. I'm going to treat this with magnesium. I'm going to write down a solvent for fun. I'm going to put diethyl ether, and that's going to give me my Grignard reagent. So let me just scribble all that down. like this, and I'm going to draw the charges here. So here's my Grignard. And so in the last two steps, first I'm going to treat it with acetone, ketone, right? Again, because this is going to act as a nucleophile on the ketone. And then in the very last step, you can treat it with water or aqueous acid, and that's all there is to it. And thus, it's nothing more than some regular old Grignard chemistry. This is all just regular old Grignard chemistry. The difference is that you have to recognize that since you have an alcohol in here, if you were to just try to make a Grignard with that, the Grignard is going to deprotonate the proton off, or remove the proton from the hydroxyl, and you're going to destroy your Grignard reagent. This is a really common question that I used to use on quizzes. I don't know if I do it on the quizzes in the summer course. However, it's a, I'll put here quiz question. I know I've used this question before. So quiz question, we'll put down here question mark. Maybe yeah, maybe no, but I think it's a very good question. Is everybody with me on that? Give me a thumbs up if you follow me. And if you have a question, don't hesitate to ask. Is everybody with me? There we go. Okay. It's funny because do we need to include TBAF at the end? Yes, Emily, I left it out, didn't I? So let's throw that in, Emily. Mr. Dion's losing it. So what did I do here? Yes, I protonated, and well, I guess, technically, Emily, if we're using H3O plus, it should remove the silyl ether, but let's just pretend it didn't. Let's pretend it was so weak of a buffer that it didn't deprotonate it. So let's throw that in here, TBAF, to do the deprotonation. There, I think that's a lot better. Okie doke. The next section, 12.8, deals with the preparation of phenols. We skipped this section because it's not covered on an ACS final. However, I will just talk about it really briefly here. It says that 2 million tons of phenol, which is this compound here, we talked about this last class, are made yearly. So very important compound. You have to know phenol to be an organic chemist. And acetone, we even use that in the lab to clean our dishes sometimes. Well, those are made from benzene. What we do is we take benzene and we treat it with propylene and phosphoric acid, and that does what's called an electrophilic aromatic substitution reaction. That's covered in chapter 16, 17, 18, something like that. And we end up making this compound here, which is called cumene. Reason I'm putting a highlighter around this compound is because we end up using cumene as an intermediate. In some of the chapters, we must use it 20 times as an intermediate. And I always call it, with my students, I always end up calling it isopropyl benzene, which is a totally reasonable name. But cumene is the common name, and I think it's wise to know that. So what they do is oxidize cumene to make a hydroperoxide, and then treat that with aqueous acid, and you end up producing phenol and acetone. And acetone, besides being a paint thinner and paint remover and nail polish remover and dishes cleaner and a solvent, phenol is used in a whole bunch of things. Okay, phenol is found in all kinds of glues and adhesives. It's used as a monomer to make different polymers. It's used to make some drugs, all kinds of different things for phenol. So now you know where phenol comes from. It just comes from benzene, and when they make phenol, they also end up producing acetone at the same time. Let's move on to section 12.9. So take a little breather here, section 12.9, which deals with some reactions of alcohols. There's a whole bunch of different reactions in here, and I'm going to be very clear with you which mechanisms you need to know and which ones I'm not going to ask you and won't show up on an ACS final. There's some new reagents in here, but there's also some review in here. For example, if you looked at this slide already, you might have said, well, I've already learned both of the reactions on this slide were covered in chemistry 3101, and you'd be 100% correct. We learned that when you take a tertiary alcohol and treat it with hydrogen bromide, you can end up producing a tertiary alkyl halide, and that is formed via an SN1 process. The first step is you take that tertiary alcohol, and we know that an alcohol is a horrible leaving group, a hydroxyl, and so we protonate that to form an oxonium, and the oxonium is a dandy leaving group because water is the conjugate base of hydronium, which is a strong acid. Then we produce a carbocation, and the bromide can come in as a nucleophile to make an alkyl halide. So again, we get an alkyl halide from a tertiary alcohol. If we use a primary or secondary alcohol with HBr, it proceeds similarly, but by an SN2 mechanism. In the first step, we transfer a proton in order to convert the hydroxyl into a good leaving group. So here we have a good leaving group, but then we get the nucleophilic attack and the loss of leaving group occurring simultaneously. And so this is an SN2, whereas when we have the loss of leaving group and nucleophilic attack occurring stepwise, this is an SN1, SN1 at a time, and then SN2 for SN together. So again, these are nothing more than reactions that we covered in Chemistry 3101. Well, if you want to make a primary alkyl chloride, you can't just use HCl. It doesn't work. It works with HBr, but not with HCl. So how do we spruce up the reaction conditions? What we do is we have to add zinc chloride. Why do we do that? We do it because zinc chloride is a Lewis acid. And you might remember that the definition of a Lewis acid is an electron acceptor. So when the Lewis acid gets attacked by the hydroxyl, which is a nucleophile, it ends up making a positive charge on the oxygen in the Zwitter ion, which renders the alpha carbon more electrophilic. I don't know what happened there. Electrophilic, and thus it is more susceptible to nucleophilic attack by a chloride, which isn't as good a nucleophile as a bromide. It's smaller, it's not as polarizable. And so it's similar, but again, a little bit different in that we have to add in that Lewis acid to promote the reactivity or to enhance the reactivity, which then promotes the nucleophilic attack to make a primary alkyl halide. I'm going to put on here, know this mechanism. It's only 3 curved arrows, so I think it's totally reasonable. And it also will help you to remember that you can't just use HCl. You have to use HCl and zinc chloride as a Lewis acid to convert a primary alcohol to a primary alkyl halide. Well, on the next slide, I have some more review. If you go all the way back to chapter 7, way back in chapter 7, we talked about another way to make an alcohol a good leaving group, and that is to convert it into a tosylate. How do we do that? We treat it with TSCl. So TSCl stands for tosyl chloride, which in tosyl stands for toluene sulfonyl chloride. And then PY, of course, stands for pyridine or base. So we end up forming the tosylate, which is a good leaving group. And then our nucleophile is going to attack via a backside attack. So this would be backside attack. And so we get our alkyl halide formed, but we end up with inversion of configuration. We see that right here. In the first step, we treat this R2-butanol with tosyl chloride and pyridine to make the tosylate. So that's what we make in the first step. But then the bromide from sodium bromide comes in and it attacks from the backside. And we end up with S2-bromopropane. Again, inversion of configuration with this reaction. The next slide shows a couple of new ways to take primary and secondary alcohols and convert them into alkyl halides or alkyl bromides. Again, you have to know that these reagents are used to make or used with primary and secondary alcohols. These reagents are SOCl2. SOCl2 stands for thionyl chloride, or that's the name of it. And thionyl chloride has a Lewis structure. Looks like this. I'm going to put in all the lone pairs here. It's in another slide. Okay, we can use thionyl chloride and pyridine to take an alcohol and convert it to a chloride. Or you can use phosphorus tribromide. With a primary or secondary alcohol, and that will convert it to an alkyl bromide. I don't ask my students to know the mechanisms for these, but the mechanisms are shown here. I'll scribble it in here. I'll just put will not ask mechanism. I'm not going to write do not need to know because you need to know everything, but will not ask mechanism. However, the mechanism for the formation of a chloride from thionyl chloride and pyridine and a bromide from phosphorus tribromide, they both have something in common. And what they both do is they end up taking a bad leaving group, the hydroxyl, and converting it into a good leaving group. So we have the hydroxyl reacting with the thionyl chloride, then a loss of a chloride and a deprotonation to make this good leaving group. And then the chloride can come in as a nucleophile, and we end up producing sulfur dioxide as a side product. And sulfur dioxide is a gas, and so the gas is going to end up going up the smokestack, so to speak. And so based on the Chatelier's principle, this is going to be an irreversible process. If we look at the reaction with phosphorus tribromide, we have the same thing occurring where the hydroxyl, which is a bad leaving group, gets converted into a great leaving group. We have the hydroxyl attacking the phosphorus of PBr3. We form this good leaving group, and then the bromide, comes in an SN2 reaction, displaces the good leaving group, and we end up forming the alkyl bromide. And this guy here, this is called dibromophosphonous acid. I'll never ask you that, but I'll put here as well, will not ask mechanism. All right. Well, let's take a look at some other reactions of alcohols, namely elimination. This is one of my favorite reactions in organic chemistry. It's got such good atom economy and it's so easy to do. Again, if you need more background on this reaction, it would be found in chapter 7, section 7.10. If you take a tertiary alcohol or an alcohol and you treat it with concentrated sulfuric acid and heat it up, that's going to affect an elimination and remove water to make an alkene. Now, since we have a tertiary alcohol, here that reaction is going to proceed via an SN1 mechanism. In the first step, we protonate the alcohol to make a good leaving group. That leaving group is going to leave to make a carbocation, and then a proton that is alpha to the carbocation can be removed to make an alkene. This is a mechanism you must know. Again, this is covered in chapter 7, way back in Organic Chemistry 1. However, when we do this reaction here, the only possible regioisomer you could get is this one. If you have a tertiary alcohol that can give you a mixture of regioisomers, the more substituted alkene is always going to be the major product. You can get the Hoffman product. So this is the Hoffman product here. You can make that. However, if you wanted to make that less substituted alkene, which is the Hoffman product, the best way to do that would not be an E1 reaction, but an E2, and where you would first treat the alcohol with tazol chloride and pyridine to convert it into a good leaving group. And then in the second step, you treat it with a bulky base like potassium T-butoxide to give you the Hoffman product or this exocyclic alkene. Well, with all that information in mind, let's see if we can identify some reagents that we would use to affect these transformations. Oops, there we go. So 12.19a, we're taking a secondary alcohol and we want to convert that to an alkyl bromide. Well, does anybody have an idea of a way we could do that? There's two possible ways we could do that based on what we looked at today and previously, really, in Organic Chemistry 1. Anybody have an idea how we might do this one? What's a reagent that I just showed you? Just one reagent that would take you from the alcohol to the alkyl bromide and would effectively do the reaction with an inversion of configuration. What about phosphorus tribromide? Right? Because remember, phosphorus tribromide converts the alcohol into a good leaving group, and the second step is an SN2 glyphilic attack. And so that occurs via a backside attack. So we end up reversing the stereochemistry. And thus for this one, you could use PBr3, or another option would be to first convert the alcohol into a good leaving group using tazol chloride and pyridine. And then you could do the SN2 using sodium bromide. Right? Bromide would be your nucleophile. The next one, we want to take a tertiary alcohol and convert it into a tertiary alkyl halide. Well, I think the best way to do that would be with just plain old HBr. That's a reaction that we learned in Organic Chemistry 1, and this is an SN1 mechanism. Back here, this was an SN2 for either of these. The next one, we're taking a secondary alcohol and we're converting it to a secondary alkyl chloride. Well, we've got a couple of ways to do that. We could use thionyl chloride and pyridine. That would be one way. So SOCl2 and pyridine is one way we could do that. Or we could use the way that we learned in Organic Chemistry 1. First, we treat it with tazol chloride and pyridine, and then we would treat it with sodium chloride. Chloride would be our nucleophile. And for the last one, and again, both of these would be SN2 mechanism. And for the last one, we want to take a secondary alcohol and convert it to a secondary alkyl bromide. I'll just put the best way to do that would be with PBr3. It works well with primary or secondary alcohols. And there you have it. All right, there we go. I think that's good for all of those. Let's move on to the next question. It says predict the products of the following transformation. We're taking a tertiary alcohol, and we're treating it with sulfuric acid, and we're heating it up. So that's going to cause water to be removed or eliminated from the molecule. And since we're heating that up, the major product is going to be the Zaitsev product. So this is our Zaitsev product, which would be the major product. But we're also going to get some of this product, which would be the minor product. And this would be the Hoffman, which is the minor product. And there you go. And both of these are going to occur via E1 mechanism. So we have E1 for both of those.